So it's a pleasure for me to take part in this meeting. Gives me a chance to remember the day many years ago when Boaz kindly invited me to give a talk at Tel Aviv University. It's a good memory. My talk is about logic programming systems called answer set solvers. Their functionality is somewhat different from the functionality of prolog systems that are better known in the world of logic programming. Answer set solvers are software systems that find stable models of a logic program. And I'll define stable models a little later. The first thing I want to do is to give an example. So here on the left, you see a logic program which consists of three rules: P if Q, Q if not R, R if not P. And if you give this logic program as input to an answer set solver, for instance, the solver that I used here is called Klingo, it will produce as its output two answers, which are, according to the definition that you'll see soon, are the stable models of this logic program. To compare the operation of answer set solvers with operation of prolog systems, I can say, first of all, that a traditional prolog system expects a logic program with unique stable model. So this particular program would not be a good input for prolog. If you give it to prolog, it will loop infinitely. And then what a prolog system expects, in addition to a logic program, also queries. And a response to a query is an answer to a query is a member of that unique stable model that has a special syntactic form described in the query. So that's where the difference is. And one other thing I wanted to say before I give the definition of a stable model is why answer set solvers are important and why much attention was given in recent years in creating these systems. They are useful because they serve as a basis, as a main computational tool in this programming methodology, which is called answer set programming. And the idea of answer set programming is when you have a search problem, you represent it, encode it as a logic program, so that this problem is encoded as the problem of finding a stable model of that logic program. And then you run an answer set solver to find the solution. In other words, this approach to search is similar to the approach to search based on set solvers that Moshe talked about earlier today, except that instead of clauses, we use rules, and instead of satisfying truth assignments, we represent solutions by stable models. And this approach has found many applications in many areas of science and technology. I just listed here a few topics, a few applications mentioned in a recent talk at a logic programming conference. So what we are going to talk about is what stable models are. And let's go back again to this example that you saw in the first slide. First of all, in our definition of a stable model, we'll think of rules in a logic program as propositional formulas. So that this colon dash symbol, we'll think of it as implication written backwards, and we'll replace N or T by the usual negation sign, so that this logic program here can be represented as this set of three implications. And if we look at the truth assignments that satisfy these three implications, the models of the set of formulas, we'll see that there are 4 of them out of 8 ways to assign truth values to PQR. There are 4 that satisfy all 3 formulas, and we'll represent these models by sets of atoms. Every truth assignment will be represented by the set of all atoms that get the value true. So this singleton R, for instance, is the truth assignment that makes R true and makes P and Q false. So if you compare this set of models of our set of formulas with the set of answers produced by Klingo with the set of stable models, you will see that what Klingo returns is the first 2 of these 4 models. And what the definition of a stable model is going to tell us is how these 2 are different from the others, in what sense they're stable. And there is one case when the definition of a stable model is particularly simple. It's the case when our formulas that you deal with are definite clauses. In other words, when each of the formulas is an implication with an atom in the consequent, and a conjunction of atoms possibly empty in the antecedent, as in this example, for instance. Any set of definite clauses has a unique least model. It's actually the set of all atoms that can be derived from these clauses. And it's a least in terms of set inclusion. It's a subset of every other model. And in this case, this least model is the unique stable model. So here you see this set of 3 formulas written in the format that Klingo understands, and that's the answer that Klingo will produce. Now, the general definition deals with arbitrary sets of propositional formulas. So I'm going to define when a set of atoms is considered a stable model of a given set pi of propositional formulas. And this definition is based on this auxiliary definition of the reduct. So what we'll define first is when we are given a propositional formula F and a set X of atoms, how we reduce F with respect to X. This process of constructing the reduct consists in identifying the subformulas of F that are not satisfied by X. Among those, we only take the largest subformulas, maximal, that are not contained in the even larger subformulas that are not satisfied by X. And then we take each of these subformulas not satisfied by X and replace each of them by the falsity symbol bottom. So here you see, for instance, what happens if we take the formula not P implies Q and calculate its reducts with respect to all 4 subsets of the set of atoms that occur in it. If, for instance, we want to reduce it with respect to this set, the empty set, in other words, the truth assignment that makes both P and Q false. Here, the whole formula not P implies Q is false. That's the maximal subformula not satisfied by X. So the reduct is falsity. In the second line, the largest subformulas that are not satisfied by X, if our truth assignment makes P true and makes Q false, if these are not P and Q, so you replace each of them by falsity, and that's the set that you get, and so forth. And now we say that X is a stable model of pi if X is minimal with respect to set inclusion among the models for the reducts of the element of pi. So for instance, this set that we used in the third line, singleton Q, it's the only stable model according to this definition of this formula, not P implies Q. Indeed, let's look at at these reducts again. In the first case, for the empty set, this reduct is unsatisfiable. So of course, not P implies Q is not a model of this. The set has no models. In the second and fourth line, our reducts are tautologies. So not P implies Q. So this singleton Q does satisfy them, of course, but it's not minimal because the minimal model of the tautology is the empty set. And it's a third line. It's the place where we have this complete match, because the reduct, which is equivalent to Q, has the singleton Q, the set that we started with, the set X that we used to construct the reduct, is its minimal model. So when we have such a match between the set that you started with and the modulus of the reduct, that means that our model is stable. So you can see the definition of a stable model uses a kind of a fixed point construct. It tells us how to check whether X is a stable model. You construct the reduct and then you check whether it's a minimum model of the reducts of the elements of pi. And the question that we're going to address is how to find stable models of a given set of formulas. And we'll talk today about one of many available approaches to this problem on what is called set-based approach to answer set programming. As we discussed, the problem of finding stable models is somewhat similar to the problem of finding satisfying truth assignments for a set of clauses. And there are actually, there are cases when actually the problem of generating stable models of a program can be simply reduced to the problem of finding a satisfying interpretation for a certain set of clauses. And in this case, we can calculate stable models by forming the set of clauses and then running a set solver on it. And the most basic, the simplest form of this set-based approach is to form what's called programs completion. There are cases when programs completion is the set of clauses with this nice property that its models are exactly the stable models of a given program. I'll define programs completion and tell you more about this method on the next slide. But before I give you a few dates to illustrate how this whole area was developing. So the list models of definite clauses, the easy case, were introduced in 1976. Completion was defined first in 1978 for a special case. And then it was made somewhat more general and led to the definition that you'll see on the next slide in 1984. Stable models were originally defined for program for formulas or rules of a simple form in 1988. And then the definition that you saw in the previous slide was proposed in 2005. The first result relating stable models to completion that could be used for the design of set-based solvers, as we realized years later, was found in 1994, and the more sophisticated form of this relationship that significantly extends the class of programs for which stable models can be defined using this method was found in 2002. The first answer set solvers was created in Finland in 1997. The first set-based solvers in US and in China in 2002. And my favorite solver, Klingo, that I mentioned before, in Germany in 2007. So what is program completion? We'll define completion not for arbitrary sets of propositional formulas as stable models, but for a special case. when our set is finite, and when every element of the set is an implication with an atom in the consequent, and the antecedent can be an arbitrary propositional formula F. The completion of such a set pi is the set of equivalences, one per atom in the underlying signature, one per atom occurring in the program. These equivalences are called completed definitions of these atoms. So the completed definition of A says that A is equivalent to the disjunction of the antecedents of all the implications that have A in the consequent. In other words, if you think of each of these formulas with A in the consequent as sufficient condition, as giving a sufficient condition for A, the antecedent of this implication, then what this completed definition says is that collectively these sufficient conditions are also necessary. A is true only if it is supported by at least one of these sufficient conditions. The completion of pi is stronger than pi. It entails pi clearly, because if you look at these equivalences left to right, the implication from this disjunction to A is exactly the conjunction of all the formulas in pi with A in the consequent. Now let's look at two examples here. This is again the three formulas that you saw in the very first slide. And this is a particularly easy case for constructing completion, because here every atom is the consequent of exactly one implication. So each of these disjunctions in the right-hand side has a single disjunctive term. To form the completion, you simply replace all implication signs by equivalences. And if you look at the models of this set of equivalences, which is a little stronger than pi itself, you'll see that this set of models has this completed set of completed definitions has two models, and they're exactly the stable models of this set. So we see this match, which shows that completion is maybe promising as a tool for generating stable models using set solvers. And the second example, you have here two actually definite clauses. Forming the completion here is a little more involved, because here P is the consequent of two implications. So in the completed definition for P, we have the disjunction of these two antecedents Q and R. On the other hand, Q and R are not, do not occur in the consequence of implications at all. So the disjunctions for Q and R become empty. So that these are the completed definitions of Q and R. They are equivalent to the empty disjunction falsity. And here again, the model of this completion has only one model, which is the least model of this set of clauses. Unfortunately, generally, life is more complicated. So generally, if we have any finite set of implications with an atom and the consequent, every stable model of it is a model of completion, but not necessarily the other way around. And here you see three examples showing that the converse does not necessarily hold. So look at this set of these two implications. If we construct its completion, you'll see a set of equivalences that has two models. It's satisfied if P, Q, R, all of them are false. And also if P and Q are true and R is false. But out of these two models of completion, only the first is a stable model. The second is not stable. Indeed, if you go back to our set pi and construct the reducts with respect to PQ, the only subformula of these formulas here that needs to be replaced by falsity is R. All other subformulas of these formulas are satisfied by the truth assignment that makes P and Q true and makes R false. So that the reduct is the set of these two implications. And PQ is not the minimal model of this set. You could make both implications true if you take the empty set, make P and Q false. So here we have this mismatch between completion and stable models. And here you see another similar example. This mismatch can happen even when our implications are definite clauses. The completion of this set has two models, and the second is not minimal. In this case, there's only one stable model, of course, because the clauses are definite, and that's the minimal model P. So this is what this old 30-year-old theorem by Fash tells us. It describes condition actually for sets of formulas where F is of this form, where F is a conjunction of literals. It gives a condition which guarantees this complete match between stable models and models of completion. And what I'd like, and after this first condition was found, there have been several publications by many authors who proved other theorems of this kind, other Fage-style theorem, I would say, that describe the relationship between, that describe cases when completion and stable models are identical. And in particular, one direction of work was to extend it to rules of a more complex form than in the original condition. And what I want to show to you is a recent result of this kind. What this theorem says is that if you have this finite set of propositional formulas of this form where F is arbitrary, what you can do is to form what we call the positive dependency graph of pi. It's a directive graph such that its vertices are the atoms occurring in pi, and the edges are organized in the following way. You take the rules, these formulas, implications in pi, and in F, you identify all atoms A prime that occur in F strictly positively. In other words, so that within F, this A prime should occur not under any negation and not in the head of any implication. So this is a little stronger than the definition of being a positive. A positive occurrence is an occurrence that occurs within an even number of negations or antecedents of implications. Here we want this number to be zero, strictly positive. And for every such A prime, you include an H from A to A prime. And the sufficient condition that given by this theorem is that this positive dependency graph is cyclic. If it's a cyclic, then not only stable models are models of completion, but also the other way around, models of completion are stable. And here you can see examples, our 4 examples with positive dependency graphs for them. And you see that in the first 2 examples, when you'd have complete match, the graph is a cyclic. And in the last 2 examples, you have these loops, edges from P to Q and from Q to P, and here from R to Q and from Q to R. So this example illustrates the use of these positive dependency graphs as a justification for running a set solver to calculate stable models. Thank you for your attention.
Thank you very much. Questions? No.